Well, greetings. My name is Tom Irvine, and we're going to be talking about sine sweep vibration today. And again, this series of presentations is being sponsored by the NASA Engineering and Safety Center, NESC. So, why would we ever do a sine sweep test? Well, there's different types of situations. We might, for example, be doing a modal test where we have a small electromagnetic shaker attached to a test article via a stinger, and we could use a sine sweep test for modal testing. But in this class, we're going to be more concerned about what if we have a large shaker table and we're using that shaker to apply a base excitation to an avionics box or subsystem or some other piece of equipment. Now, there's many different reasons for doing sine sweep vibration, but perhaps one of the most common is to identify the structure's natural frequencies and amplification factors or the equivalent damping ratios. And in some cases, maybe we have a random vibration test as the main test. Well, we can perform sine sweep both before and after the random vibration test to determine if any parts have loosened or if there's any changes in the materials or some nonlinearity, for example. And of course, we can also use sine sweep for linearity tests where we, for example, might start off with some low-level base input, maybe a half of a g acceleration. Then we could step up in 6 dB steps and do test at 1g and then at 2g and 4g and so on. And there's different things that can happen if the natural frequencies, the response frequencies of our structure are changing. That could mean that the stiffness is changing. And also it's very common for damping to be nonlinear. And the classic example would be, let's say we have a structure, piece of equipment that has some joints. Well, at low level amplitude inputs, those joints remain fixed. There's no relative motion in the joint, and the damping is very low. But then at higher levels, those joints start to have slip, and the slipping effects cause the damping to increase. So damping could increase as we go up in level. And there's all different types of scenarios that could happen with both stiffness and damping. Sometimes we use sine sweep, and this is more so from a historical perspective. Sine sweep is used as a workmanship screen to detect latent defects, such as defective parts and solder joints in an avionics box. And there are some cases where sine sweep represents an actual vibration environment, and later on we're going to be talking about how solid rocket motors have potentially have thrust oscillation effects, where standing waves, pressure waves, get set up in their combustion cavities. And this can actually make a sinusoidal oscillation, and in many cases, the sinusoidal oscillation will sweep downward in frequency with time. We'll talk more about that later on. And then the NASA Goddard Space Flight Center typically uses sine sweep vibration for spacecraft testing. On the other hand, NASA JPL, the Jet Propulsion Laboratory, would typically use random vibration testing. And later on in this series of presentations, we'll talk more about the differences between sine and random and the different trade-offs between using the one over the other. So this chart here, this is just for academic purposes only. This is to give you a conceptual idea of what a sine sweep is. So along the y-axis, we have acceleration in g, and along the x-axis, we have time in seconds. So this is an acceleration time history. And we start our sweep in this case, in this example, at low frequencies. And as time moves forward, these waveforms become increasingly compressed. And not the natural frequency, but the excitation frequency is increasing. So our excitation frequency is increasing as time passes by. Now, one of the essence of sine sweep vibration is that any given instant in time, there's only one excitation frequency. But that the frequency of the excitation is continually shifting with time. Now, we could also talk about how our equipment responds to this sine sweep. And even though there's only one excitation frequency at a given instant, there could be one or more or two or more natural frequencies or modes, natural modes being excited. And that would typically be the case if there was two modal frequencies that were closely spaced with one another in terms of frequency. And as the sine sweep passes nearby, maybe two modes would be excited in varying degrees. But for many structures, the natural frequencies might be well separated by an octave or so. In that case, typically there might only be one response frequency of interest at a given time. Okay, I think we've covered this chart already. Well, I'll add a little bit more to this. In this case, we've started at a low frequency and we've swept upward to high frequency. We could have done this backwards. We could have started at the high frequency and swept down to the low frequency. Or another thing that's often done is we might have a series where we'll first sweep low to high, and then we'll immediately go back downward from high to low. And then we might actually repeat, several cycles of both going high to low, then, of going low to high and then back down to low again. You'll see some specifications written like that if you look at enough sine sweep specifications. Okay. We also need to talk about rate. So that the two typical ways are to either perform a linear sweep rate or a logarithmic sweep rate. And the more common of the two is the logarithmic sweep rate. And the sweep will spend a greater amount of time at the lower frequency end if the sweep is logarithmic. And the example in the previous figure was in fact a logarithmic sweep rate. And the previous example had a constant amplitude, but the amplitude of a sine sweep specification can change as a function of frequency. Now back to this logarithmic sweep rate. So imagine a cycle of vibration, one cycle of vibration at low frequency. And then imagine one cycle of vibration at a high frequency. Well, at the lower frequency, it takes a longer duration to reach one full cycle. And that's kind of the idea behind the logarithmic sweep rate, is we want to spend proportionately more time at the lower frequencies in order that they can achieve, say an even number of cycles per frequency band throughout the frequency domain. Let's go to an example here. Let's say a vendor has a product and it must withstand a sinusoidal vibration with an amplitude of 12 G per the test specification. So the desired frequency domain in this case is going to be 10 Hertz to 2000 Hertz. And our shaker table is going to have a displacement limit of 1 inch peak to peak or 0.5 inches zero to peak. So as you should remember from the previous unit, the displacement is a concern at low frequencies, and this could cause us to have a constraint on our vibration specification. So how should we do our specification? Well, the answer in this case is to use a spec with two amplitude segments. And the first is going to be a constant displacement ramp, and the second segment is going to be a constant acceleration plateau. So this is our sine sweep specification example. And the y-axis is acceleration in G. The x-axis is frequency in Hertz. This slope here is a ramp with a 1 inch peak-to-peak displacement. And then we have our 12G plateau. Now the point at which these two lines intersect is called the crossover frequency. And the crossover frequency is the frequency at which a 1 inch peak-to-peak displacement will correspond to a plateau of 12 Gs. So how do we calculate a crossover frequency? Well, in this case, it's going to be 15.3 Hertz for the previous example. And what we're going to do is we're going to take our peak acceleration and divide by our peak displacement. And we need to be consistent and think about units and dimensions. So in this case, we're going to have 0 to peak amplitudes for each of those two metrics. And if we have acceleration in g's and we have displacement in inches, for example, then we need to account for a factor of 386 inches per second squared per 1g. So we make this ratio, we take the square root, we divide by 2 pi, and that's going to be our crossover frequency. Now, here's the vibration data signal analysis package that we've been using throughout this course. And even if you already have version 2.9, please go back to the vibration data WordPress blog and download the most current version, because some of the subprograms that this refers to have been updated as well. And by the time you actually view this presentation, who knows, vibration data.m may be at version 4 or 5 or whatever. But let's go to a miscellaneous function, and it's going to be the sine sweep parameter function. All right, so let's begin that. We're going to calculate crossover frequency, and we're going to, let's do displacement peak to peak to acceleration. We're going to have English units. So we have 1 inch peak to peak displacement. That's our limit for our shaker. Our acceleration is going to be 12 Gs. And we calculate 15.32 Hertz as the crossover frequency. And in a minute or two or so, I'll go back to the chart and show you that. There's one other thing I want to take a look at while we're here. Let's go to our miscellaneous functions, and we can go to amplitude conversion utilities. So we're going to go steady state sine amplitude. Click on that. Our displacement is going to be 1 inch peak to peak. Our frequency, this is going to be the lowest frequency of the spec, the starting frequency at 10 Hertz. And we can see the equivalent amplitude metrics. And 5.1 G is the acceleration that we can achieve at 10 Hertz for a 1 inch peak to peak displacement. So let's go back to our specification on our previous slide. So we have our crossover frequency at 15.3 Hertz, so we know how to calculate that. And then we have 5.1 G. That's going to be an acceleration at 10 G per this displacement constraint. Another thing we want to look at is the number of octaves. And how many octaves are there from 10 to 2000 Hertz? Well, if we double the frequency, that equals an increase of 1 octave. So let's say we go from 10 Hertz to 20 Hertz. That's a 1 octave step. Or if we go from 20 Hertz to 40 Hertz, that's an octave step. So from 10 to 2000 Hertz, how many octaves do we have? Well, here's how we can step up. So 10 to 20 Hertz, that's 1 octave. And a second, third, fourth, fifth, sixth, seventh, eighth. Well, 2000 Hertz is more than 7 octaves, but it's less than 8 octaves. So how many octaves is it? Well, what's the formula? So here we have, these are going to be natural logarithm terms. If we take our upper frequency, 2000 Hertz, divide by our lower frequency, 10 Hertz, take that ratio, take the natural logarithm, divide by the natural logarithm of 2, that's our number of octaves. So it turns out the frequency domain from 10 to 2000 Hertz has 7.64 octaves per this formula. And as you might be anticipating already, we have a way to do that in the vibration data GUI package. So let's go to sine sweep parameters, and then we're going to calculate the number of octaves. And we're going from 10 to 2000 Hertz. And there are, in fact, 7.64 octaves in that frequency domain. Okay. Very good. Let's move on now. Okay. So the reason we want to calculate the number of octaves, the main reason is we want to compare that to the sweep rate, especially if it's a logarithmic sweep rate, and determine the test duration. So a very typical sweep rate for sine sweep testing is 1 octave per minute. And if we sweep at that rate or at a lower rate, that will give the oscillators, the hypothetical single degree of freedom oscillators that are responding to the sine sweep, a chance to peak out. In other words, to undergo sort of a quasi-steady state resonant effect. So if we have 7.64 octaves and our sweep rate is 1 octave per minute, then we're going to have a duration of 7.64 minutes or 7 minutes 38 seconds for one sweep. So that's just some examples on sweep rate. Another way to specify sweep rate is we could say, okay, we're still going to test from 10 to 2000 hertz, but we want to do it over in 8 minutes. Well, if we take 7.64 octaves divided by 8 minutes, then our sweep rate would be 0.955 octaves per minute. And if you go back to the sine sweep parameters and begin miscellaneous analysis, there's some things you can do with sweep rate and total sine cycles, and I'll let you play with that on your own. It's pretty straightforward. Okay. Next up, we're going to actually synthesize a sine sweep time history. That's one of the fun things we like to do in this class, is we like to synthesize time histories. And in our previous unit, excuse me, here I get organized here. In our previous unit, we synthesized a sine function. So let's go to vibration data, and this time it's going to be a sine sweep. So we're going to go to generate signal under miscellaneous, and it's going to be a sine sweep. Linear sweep, no, let's change that to log. Sweep upward in terms of frequency, yes. 2 coordinates. For this example, we're going to do, it's just going to be a flat plateau. 10 hertz, 80 hertz. Then we have 1G, 1G. Now 1G is low enough so that at 10 hertz, we don't need to worry about the displacement. Our sample rate should be at least 10 times higher than the maximum frequency. We'll talk more about the rule of thumb or criteria for that later on. And I'm going to actually make it even higher. I'm going to say 2,000 samples per second, which is equal to 2,000 hertz. Duration, okay, this is going to have a span of 3 octaves. So 10 to 20 to 40 to 80, that's a 3 octave span. We can do 1 octave per minute, so it's going to have a duration of 180 seconds. We're going to calculate, and we get a big blue bar here. And I'm going to go ahead and save this under sine sweep for our internal Matlab workspace purposes. So here we just have this big blue box here. It's filled with a solid color, but in actuality, there is an underlying sine sweep. It's just at such a long duration, it takes a couple of zoom in steps to actually see the sine function there. So this is actually the sine sweep function, I should say, where the frequency is constantly changing with time. It's increasing the time in this case. Now there's a number of things we can do with this sine sweep, and I'm going to do a Waterfall Fft Fourier transform. And later on we're going to be talking about Waterfall FFTs in earnest. But let's go ahead and start using it right now just for fun. Waterfall FFT under Select Analysis. We have our array preloaded in Matlab. It's called sine_sweep. It's acceleration G. And I probably should read the instructions here to you first. This script calculates the Waterfall FFT of a time history. The input array must have 2 columns, time in second and amplitude. The user may choose to perform the analysis either over the entire duration or over a smaller segment. Well, we're going to do the whole 180 seconds here. The plotting frequency, we're going to go 10 to 80 hertz with no overlap. we have to view our processing options, and more about those later on. Okay, there's our time history again. It's that same solid blue box, but it's really a sine sweep. And we're going to choose, let's see what we want to do here. Let's choose this one here. This is going to be 21 segments, 8.192 seconds per segment, delta F of 0.1221 Hertz. There's always trade-offs. If our time goes up, our frequency goes down, and vice versa. So typically, if we're doing this in earnest, we might play around with a couple of different cases or so. But anyways, that's going to be case number 11. Let's go ahead and calculate that. And the first curve, the graph that comes up, is called a spectrogram. And a spectrogram is the favored function for people that study human speech and also people that study bioacoustics like bird calls. So in this case, we've got time in seconds and frequency in hertz. And we can see this line here. If we drew just a smooth line through the bright colors here, it would be a curved line. And the fact that it's curved is due to the fact that we have a logarithmic sweep rate. If this were a linear sweep rate, this would just be a diagonal line. But it's not. It's a logarithmic sweep rate. So the point is that we're spending proportionately more time down at the lower frequencies. And there should actually be a 0 here, both for 0 seconds and 0 hertz. So that's the spectrogram. And the format I actually prefer is called a Waterfall Fft. And we can play around with this Waterfall Fft. We can zoom in and rotate and do different things with it. So it's sort of fun to play around with these. But here you can see again, if we were to draw a smooth line through the center of the peaks here, through the center of each peak cluster, it would be a curved line. And again, that's due to the fact that we've got a logarithmic sweep rate. So we've got magnitude along this axis here. We've got time in seconds and frequency in hertz. And let me just play around with this a little bit more. Maybe what I need to do is reset view. Okay. So that's the Waterfall Fft of our base input sine sweep that we're going to apply to an avionics box. So let's go ahead and return here. We need to talk about how we're going to apply this to our avionics box. So let's go back to the slides here if I can get myself organized. We're going to apply this sine sweep as a base input to a single degree of freedom system, and it's going to have a natural frequency of 40 Hertz and a Q value of 10. So how will our single degree of freedom system respond? So let's see what the next slide shows for us. Well, here's the sine sweep that essentially the one we just generated or synthesized. Now, I'm only going up from 0 to 2 seconds here, but the entire time history is 180 seconds. But this just gives you an idea that, yes, there is a sine sweep that underlies that signal. And the peak G level is 1 G, so the standard deviation is 0.707 G. And this is another Waterfall Fft of the same data. In this case, the parameters in terms of the delta F and time were different than the ones we just ran. But you can see that we do have a curved set of peaks here, and that's due to the logarithmic sweep rate. So the frequency is continually shifting upwards as time moves on. So here's our spring mass system, and again we're going to say that this system has a 40 Hertz natural frequency and a Q value of 10. So here we have the mass, we have the spring stiffness K from Hooke's law, we've got the dash pot C, the base acceleration is y double dot, and the response acceleration is x double dot. So y double dot is going to be our sine sweep. Now the equations of motions, we previously derived those in our Sine webinar, which was the webinar last week. And it would be so nice if we could solve this in terms of Laplace transforms. But I have not found a way to solve this for Laplace transforms for the case of a sine sweep. So if anyone can show me how to do that, please write up your derivation and send it to me. But let's go back to just the equation of motion. We need to derive it. And I'm not going to go through all the steps because we've covered that previously, but here are some of the highlights. We have our mass here. We have a spring force. We have a damping force acting upon the mass. And we use Newton's laws from our free body diagram to sum the forces. We define a relative displacement, which is equal to z, and that's the displacement of the mass minus the base input of the mass minus the base input. Let me say that again. Z is equal to the absolute displacement of the mass minus the base displacement. So Z is a relative displacement. So we make our substitutions, and you should remember these terms from our previous unit. And we come up with our ordinary differential equation. It's second order, it's linear, it has constant coefficients, and it's non-homogeneous. And if y double dot was a sine function, we could solve this very readily using Laplace transform. Sine sweep is again harder, as I mentioned earlier, and I haven't been able to do it yet. But the way we're going to typically do in this class is say, well, what if y double dot is just an arbitrary function? Is there some general purpose method we can use to solve this equation? And hopefully you remember that from our previous unit. Because to solve this for an arbitrary function, we need to use convolution integrals, or you might say Duhamel's integrals. And unfortunately, those are very numerically inefficient to solve. It's doable, but it's very inefficient to solve in its equivalent digital series form. So we instead use our beloved Smallwood ramp invariant digital recursive filtering relationship. And this happens to be the numerical engine that's embedded in the shock response spectrum calculation. So let's go ahead and do that for our sample case at hand. And if we go to select analysis, we can do single degree of freedom response to base input. This is the Smallwood algorithm function. So we have our sine sweep. Again, I should read the headings here. The script calculates the response of a single degree of freedom system to base excitation. The input data must have two columns, time in seconds and base acceleration. We've got sine sweep, we've got English units, natural frequency 40 Hertz, Q value of 10. That's equivalent to 5% damping. We calculate, and we get a couple of things here. We get actually over here in figure 1 is our base input again, which even though it looks like a filled-in rectangle, it's a rectangular box, it's actually a sine sweep function. And here we have our response in terms of relative displacement and our response in terms of absolute acceleration. So acceleration g versus time in seconds. I note that we have a 40 Hertz system and q is equal to 10. Now at the lowest frequencies, we have a situation where the excitation frequency is say 2 octaves or so below the natural frequency of our test article. So in this case, we have very nearly unity gain. The response acceleration is just tracking the base input acceleration. Now as we sweep upward, eventually we're going to approach 40 Hertz excitation frequency. And we get 40 Hertz excitation frequency, we're going to get this quasi-state resonant response behavior because we're matching up or coinciding with our natural frequency. So we can actually zoom in. You can see it's plus and minus 10G. And there is an underlying sine sweep signal there. So let's think about this 10Gs. If we have a 1G base input, we multiply by Q is equal to 10, that equals a 10G response. Now that's a neat and tidy rule for this resonant response case, but just sort of as a warning or caveat, we have a well-behaved single degree of freedom system. We're exciting at resonance, and this neat and tidy relationship works where we take 1G multiplied by Q, we get a 10G response at 40 Hertz, which is resonance. But if we had a beam, a plate, or shell, or any kind of multi-degree of freedom system, that neat and tidy rule would no longer work. So we'll talk more about multi-degree of freedom systems later on. And let's go ahead and we're going to save this acceleration response. I'm just going to call it response for our internal Matlab workspace purposes. Let's go back and do a Waterfall FFT on our response. So we're going to begin our signal analysis. Response is the input, acceleration in G's. Okay, again, 0 to 180 seconds. Our plot frequencies are 10 to 80 Hertz. View processing, okay, there's our input time history. Let's do case 10 here, option 10. It's going to give us about 4 seconds per segment, delta F about 0.24 Hertz. There's our spectrogram here. And let's go ahead and take a look at the Waterfall FFT. And this is actually kind of in its own way, kind of aesthetically pleasing. So here we have frequency in Hertz, time in seconds. We've got starting at 10 Hertz there. So down at the lower frequency end, we've got this unity gain thing going on. Then as we start to get closer, our excitation frequency starts to approach our natural frequency. Then we ramp up to our resonance case here. Then as we get past resonance, the response is decreasing. And what's happening is our single degree of freedom system, in some sense, it's acting like a mechanical low-pass filter. So it really wants to filter out this high frequency energy, or attenuate this high frequency energy. Now, at the low frequency, again, it has unity gain. So, but sometimes, just sort of in a rough way, we describe it, this single degree of freedom system, as also being a bandpass filter, because it's amplifying the energy in this frequency band here. Okay, so that's just some fun things you can do with single degree of freedom systems and sine sweep base inputs. Okay, let's see what we have next here. I'm going to put this aside. So here's another plot in the slides of the response, our 40 Hertz system, Q is equal to 10. And at 120 seconds, it's reaching the 40 Hertz excitation frequency. And that's when this quasi-steady state resonant response occurs. Let's talk about solid rocket motors here. Now, solid rocket motors can have pressure oscillations in the combustion chamber. So think of the combustion chamber or chambers inside a solid rocket motor as behaving like an organ pipe. So in order to excite an organ pipe, we have to pump air through it. Well, in the case of a rocket motor, we have the propellant is burning and hot exhaust gas is being generated under high temperature, high pressure. And various vortex shedding and other types of thermodynamics and gas dynamic effects can occur that can produce standing pressure waves to form in the combustion cavity, which again is behaving in some sense like an organ pipe. And when these standing waves start to set up, we might call this effect a resonant burn or a thrust oscillation. And what the tendency within these motors is that that cavity is being enlarged as propellant is being burned off. So we sometimes see the sinusoidal oscillation frequency from the pressure oscillation to sweep downward in frequency as the cavity volume increases due to the conversion of propellant to exhaust gas via the combustion process. Having said that, there are some motors with some very strange cavity geometries where anything can happen, but the more common pattern would be for that frequency to sweep downward. So here we have a cross-section of a motor here, and the dark gray is the propellant, and it's solid propellant, and from what I've read, solid propellant is kind of like the consistency of rubber, like the eraser tip on a wooden pencil. And the combustion cavities are these. In this case, there are 4 exhaust nozzles, so there are 4 cavities that converge together at an apex. But these are acting like organ pipes, and again, the standing pressure waves can get set up. And that causes excitation, which propagates forward through the vehicle, and it can propagate to avionics components that are mounted in the front end structures, the avionics cylinders in the front end of the launch vehicle. And then that propagating energy can become base excitation energy to an avionics box, say mounted on a bulkhead forward of this motor. And in fact, we've got some flight accelerometer data. So let's take a look at our flight accelerometer data from a solid rocket motor burn. So we have acceleration g's versus time in seconds. And we're going to run a new Matlab function here. It's called the time varying frequency and amplitude. So let's begin our signal analysis here. And we've got a preloaded, we're going to do an external ASCII array. It's called solid_motor.dat. This was measured on a bulkhead of a vehicle that had the particular motor in question here. And we're going to do a segment duration of 0.5 seconds. And what we're going to do is calculate descriptive statistics for each half-second interval. And the y-axis will be acceleration in g. Let's go ahead and calculate that. A whole series of plots is going to come up. Let's just go through these one by one. Well, here's the original time history. And if we just zoom in, let me zoom in on this kind of peak area here where we get the peak measurement. And if we zoom in enough times, this appears to be sinusoidal vibration. And in a sense it is, but more properly it's sine sweep vibration. You'll see why in a few charts here. This plot here shows several amplitude metrics for each half-second interval. And we have acceleration g versus time in seconds. The peak acceleration for each interval is shown here. It gets up to about 1.6 g peak. Now the average or mean value is very nearly 0, the whole motor burn. So the standard deviation RMS curves are very nearly identical, as shown here. Okay, move on to chart number 3. Now here's what the dominant frequency is doing. So within each segment, half-second segment, we can use a method like just count the 0 crossings, for example, and determine what the dominant frequency is as a function of time. And we're going to ignore parts of this curve. We're going to ignore this startup here where there was a quiet period, and this ending here where it also kind of went back to a quiet period. And for some reason, who knows why, this motor has sort of the vibration becomes more benign around 53 seconds or so. So there's not actually much happening here. So we can kind of ignore this point. It's almost, you could almost call it a dropout. But the point is, let's draw a straight line to represent this amplitude here. So our frequencies start up about 530 hertz and sweep downward to about 450 hertz over the motor burn. And again, that's because that combustion cavity is enlarging as propellant mass is burned off and expelled. We've got one more chart here. Now this is peak acceleration g versus frequency in hertz. And what this is showing us at 460 hertz, we get that 1.6 g. So that's our worst case response. So how come these dots are not, or markers, how come they're not just lining up on a horizontal line? Well, something is going on, and we're not exactly sure what it is, but I have two plausible theories, and either one or both may be correct. Well, let's go back and just take a look at our time history here. So it must be that about 57 seconds, 58 seconds, that's where we're getting this 1.6 G response, which happens to be 460 Hertz. So it could be, who knows why, the amplitude of that pressure oscillation reaches its highest at this time and at this frequency. Why is that? I don't know, but it could be. The other possibility is that as we're sweeping through the frequencies, we're exciting a structural natural frequency or structural mode that happens to be at 460 Hertz. That's also possible. Of course, I suppose both could be possible in varying degrees. So this would require some further exploration to determine what's going on. But this is the type of information that's important to know if we are to design and test an avionics box or payload to withstand this type of environment. One other thing we can do here, if we go back to our vibration data. So if we go back to our vibration data, we can do a Waterfall Fft. So we're going to have external ASCII, and it's going to be the same file, solid.motor.dat. Be acceleration in G's. Okay, this was about, I think, 43 to about 62 seconds or so. And we're going to plot from 10 Hertz to 990 Hertz. We have to look at these options again. Okay, there's our time history from our measured flight accelerometer data on a bulkhead. Okay, let's try 42 segments. That's choice 8. We're going to calculate. So there's our spectrogram here there. But I prefer to look at the Waterfall Fft. So here you can see the effect here of our frequency sweep. We're starting up at about 530 Hertz, and over time we're sweeping downwards to about 450 Hertz. Now you may ask yourselves, well, okay, there's also a row of peaks at 280 Hertz and then maybe 350 Hertz. What are those? Well, to be honest, I'm not sure. It could be some spurious electrical noise or interference. I never figured that one out. But anyways, it's kind of fun to just play around and look at the different angles, different perspectives here. And also you can see the effect of this sine sweep on the spectrogram. So we have time in seconds along the Y, frequency in Hertz along the X. And you can see the decrease in frequency as time moves forward. Okay. And I think we're about getting to the end of this presentation here. Let's do some finish-up slides here. Oops. So here's just some things we kind of already looked at. If we zoom in on the instantaneous accelerometer data, which was measured from this vehicle flight, you can see it is somewhat sinusoidal, although we now know it's a sine sweep. And what I've got here is I've just got a few homework exercises you can do on your own, where we kind of just do some similar things to what we've done already. So go ahead and do these on your own, and just have fun with it. And if you have any questions, you're welcome to contact me if you have any questions or want me to check your homework results or whatever. Just a few things, just a reminder, I encourage you to go to the Vibration Data blog and visit that. And one way you can get to it is if you just type in Vibration Data here, and go to the Vibration Data homepage. This is the classic web page. Scroll down, go to blog, and you can see the blog here. Excuse me. Okay, so if we go to signal analysis package here, signal analysis. Then we can scroll down to the entry called Vibration Data Matlab Signal Analysis Package, and you can download the main GUI script that we've been running in this class. So have fun with this. Thank you, and goodbye for now.